Okay, guys. Let's return.
Oh, yeah, you're really? Oh, it's like it's right on me. Oh, sorry, Professor.
No problem. Are you guys ready? I hope you had a good break. I hope you had a delicious break. Everybody had a delicious break? You're gonna have a delicious break. Okay, so now all we need to know, you were confused about how minus the log. You don't have to worry about understanding. You don't have to. You don't have to worry about understanding the concept behind the logarithm. Just know that the pH is negative the log of the
Hydrogen, proton,
concentration. Yeah. The three words: hydrogen, proton, concentration. Yeah. Negative log of the hydrogen proton concentration. So now since we're dealing with algorithms, that means a change of one number on the pH scale represents a tenfold change in hydrogen proton concentration. So pH 4 is 10 times as acidic as pH 5. So going 1 unit above or below represents tenfold increase or decrease accordingly. So that's the pH scale. If you below 7, you're acidic. So milk is more acidic than bread and black coffee, which are really acidic. And then you have the bananas and tomatoes, which are more acidic. Then the wine and vinegar, they are really acidic. Then lemon juice is really acidic, 2.3. Then the most acidic is gastric juice. Okay? Then the pH scale, water is basic. Egg white is more basic than water. And you have house bleach. Not that we eat that, but house bleach is alkaline. Then ammonia is obviously, that makes a lot of sense. Ammonia. And the wine has a lot of OH, hydroxyl group. And ammonia is 10.5. And then the oven cleaner is the really acidic. And then the most acidic is obviously sodium hydroxide, 1 molar of sodium hydroxide. So now there are other ways that we measure the concentration. So solutions measured in terms of their concentration of the solute. So there are several different expressions of the concentration. We can express the concentration in terms of weight per volume. Weight per volume. So that means the weight of the solute in a given volume of a solution. So the IV saline contains about 8.5 grams of sodium chloride per liter. So now we have expressed weight per volume, because weight is unit mass per volume, unit milliliters or liters. What is the difference between weight and mass again? That we mentioned earlier. What is the difference between weight and mass? Yeah. What is the difference between weight and mass? And not mass. Weight and weight and mass.
She said it. Weight and then the amount of space something takes up for mass.
Yeah, excellent. So weight is the same thing as mass, but you just multiply it by gravity. So I have the same mass on planet Earth and on the moon. But when I get on the moon, my weight is not going to be the same. Why is that? The gravitational pull for the moon is less than the gravitational pull for Earth. So we multiply different numbers. We can also do a percentage. So we might be weight of a solute per unit volume. So I can have 5% of dextrose solution. A 5% dextrose solution has 5 grams of solute in 100 milliliter solution. 5 grams of solute per 100 milliliters of solution. Might be the volume of a solute, a liquid, per volume of a solution. Volume of a solute, a liquid, per volume of a solution. Like 70% ethanol has 70 milliliters of ethanol in 100 milliliters of solution. So that shows you the different ways we can suppress the measurements of the concentration. Then the expressions of the concentrations are, for molarity, you have the number of moles of solute per liter of a solution. That represents what molarity is. So that's the number of moles of solute. So now we're not dealing with the number of grams per solution or the percent per solution. Now we're dealing with the number of moles per solution. So 1 mole is the number of grams equal to its molecular weight. 1 mole is the number of grams and it's equal to its molecular weight. So the molarity is 1 mole is the number of grams equals to its molecular weight. So the molecular weight, so we have Avogadro's number. Avogadro's number is 6.03 times 10 to the power of 23. That's a mole. So what's a mole? A mole is like a dozen. So when I say dozen, I know this means 12. What's more? 12 eggs or 12 cars? What is more? In number. It's the same. Yeah. So 12 and 12. But if I say the mass, then that's different. Because now the same thing with atoms. You have a mole of nitrogen is different from a mole of potassium because they weigh differently. So I weigh how much 1 mole. So if I need to get the mole, so 1 mole is the number of grams equal to its molecular weight. So the molecular weight of that molecule in grams will represent for me how much it weighs, like for example, the molecular weight for sodium means it means this many number of sodium ions that I weigh, and it gives me that number. So 1 gram represents this number of molecules, and that represents, so let's say I have sodium and I have potassium. 1 mole is worth that molecular weight for this number. So 12 eggs is worth 5 pounds mass, but 12 cars is 50,000 pounds. You understand? So the same thing for molecular weight. When you look at that number for the molecular weight, that number represents for me 1 mole worth so I weighed 1 whole mole of sodium, it came out to that number. 1 whole mole of potassium, it came out to that number. Clear? Is making sense? Kind of. Okay. Let's say this again. 1 mole is like a dozen. That's a fixed number. That's a standard number. So when I say a dozen of sodium, 12 sodium. A dozen of potassium, 12 potassium. But I cannot weigh 12 sodium. That's too little. But what they came up with a huge number. That's like 23 zeros. That's 6 times 23 zeros. That's more than a million, more than a billion, more than a gazillion. But they came up with the number and they standardized that number. Then they said, let's bring 6 times 10 to the power of 23 sodium atoms and weigh them. How much does that come out? And that is the molecular weight for uh, for sodium. Then they did the same thing for potassium. They brought 1 mole of potassium, weighted it, and then they wrote how much that came out. Does it make sense? Makes sense, Melissa.
Yeah.
Does it make sense?
Like that's what I'm trying to figure out. Like
What
I
is the what?
understand what you're saying, but I don't know what I'm looking at.
The 6? Yeah, that's the number. So instead of writing 6, 1, 2, 3, 4, 5, 6, 7, 8, 23 zeros. That's what it means. You guys don't know what 10 to the power of 23 means?
No, I know what that means. But what does 6.03 represent? Like, what is that?
Yeah, that's the number they came up with.
That's a formula? That's a formula?
It's not a formula. That's a number. So when you multiply, so the number is like that. 603, 23 zero. That's how it is.
So 1 mole is just 6.03. This number is just an example.
It's just a standard number. Yeah, a mole. That's how much a mole is. Yes.
1 mole 23 zeros. Is that what it is?
It's not plus. It times, yeah. Times 23 zeros. Yeah. Yeah. Yeah, that's it. Does it make sense now? It's 6. What is hard about this, guys? It's like 600. So now replace, what is 600? 600 is 6 times 10 to the power of 2.
It's not what we just wanted to know where the number 6 came from. So it's just the number they made up.
They made up.
That is
So
anytime
6.03
That's
times 10 to the
mole.
23, that's a mole.
That's a mole.
Okay.
It's just like
like a formula.
it's just like a dozen. When
So
you
it's
see
just
a
like a
dozen, you
formula.
see 12. When you see a dozen,
Okay.
so if I tell you a dozen of sodium,
Now we understand.
you will say, oh, that's 12 sodium. A dozen of potassium, that's 12 potassium. A mole of sodium, that's this number. That's how it is.
Standard.
Okay, yeah, it's a standard number. Yeah. Yeah. Okay. So body fluids usually quantified in millimolar. So that just represents for you how. I'm sorry? No, but maybe I can ask you what is this number is known as.
Can you do a different element?
A different element like.
The mole of potassium.
Okay. What's the question again?
Like a different example with a different element.
Like, what would be a mole of potassium?
So a mole of potassium is in the periodic table. So the periodic table, all these molecular weights represent a mole.
Oh, okay.
So that gram number under the sodium, that's a mole's worth. They went, they collected.
So then you would just
So
change the
potassium's mole is
6.09 to the
39.
new
To
number.
that number.
Yeah, so this is in unit mole. Okay, hold on. Grams, guys, what is gram? Gram is unit mass. So now what's the weight of this class? This weight of the class now can come out to maybe like 1,000 pounds, for example, 1,000 pounds or 5,000 pounds, for example. But now I can't tell how many people in there. So in the periodic table, if they just put for you the weight, the molecular weight, you don't know it's a molecular weight of what, but now you know it's a molecular weight of a mole. So now they weighed, so the sodium and potassium do not weigh the same. So sodium, so like I said, dozen of eggs and a dozen of cars are the same number, but they're not the same weight. So a mole of sodium and a mole of hydrogen are not going to be the same. They're going to weigh different. So they chose one big because they're so small. That's why they came up with this huge number. So now they came up with this number and then they standardized it for the whole periodic table. So now it's called Avogadro's number. This is called Avogadro's number. Avogadro number. So Avogadro's number is for each atom, and then they put it in the periodic table. Okay? Yes. Yes.
The 23 is that
No, the 23 is the zeros. So if I go like this, 500. So that's 500, right? If I want to rewrite 500, I go times 10 to the power of 2. So now this times 10 to the power of 23, that means this number you multiply by 23 zeros. Does that answer your question?
Yeah, I mean, I was just asking because I know sodium has 23, so I thought that's why they did it.
No, this is the tens. This is not the sodium has. So they weighted out this number of small molecules, and it came out to that molecular weight.
Okay, so 23 for sodium, like you're saying,
Yeah.
is that 23 equals 1 mole of sodium?
Yes.
Okay.
And not just for sodium, for all of them.
Okay.
Yeah.
So any number that, like, that's under the.
Yeah.
Okay, that's 1.
That's 1 mole.
Okay.
You got it now. Okay. Was this just even the other class? They had a difficulty. Like we spent as this much time.
No, because you know what?
Okay. Okay. All right. Okay. Okay. As long as we're through now.
Any number that.
Yeah. Okay. So expressions of the concentration. There's another form. So now it's no longer mass per volume, no more percent per volume. It's the milliequivalents per liter. So the expression of the electrolyte concentration, for example, and that accounts for millimolar concentration of a solute and electrical charge of its particles. So it's important for nerve firing, the heartbeat, the muscle contractions, and delivering the intravenous fluids. Now that's where we should have taken a break right here. But you guys were like, "Can we take a break now?" But it's okay. So wow, I don't want a ticket. I don't like getting tickets. Okay. And you know they're never gonna let you. If somebody want to give you a ticket, never say please. I'm sorry. Don't never do that. Just take your ticket and go. They will never.
You're gonna have them walking around like this.
Yeah, it's like you know when you're fishing and you catch the fish. What kind of fish do you throw it back in the sea? You will never throw it back, right? Some people do, but most of the people
I'm
don't.
gonna try something though. I think I'm gonna fix
Yeah, so don't if the cop want to give you a ticket, take the ticket and go. Don't waste your time. Okay, energy. Energy is the capacity to do work. And we already talked about this very important concept. And you're gonna see this are you guys taking the biochemistry course with physical sciences?
No, what?
Okay.
Oh, no, that's the general.
Yeah, that's
GBA.
yeah. You're not taking that?
No.
Okay.
No.
Because
No.
so why aren't you taking that?
Why?
We're doing the AAS.
What's the difference?
Yeah.
When we go probably to.
You guys associate
Yeah.
and they are bachelors?
Bachelors.
I
But
see.
they're general, like you don't have to be a nurse, you don't have to be an LPN to get a nurse.
Yeah. But for the associates, you have to be an
You
LPN.
have to be an LPN to operate the program.
And when you get the associate, what do you do now?
You can go back if you want to, bachelor's online, 3 to 6 months, right? Thank you, sir, right? Until 2027 now, we can continue.
Okay.
It's almost one.
Okay, so when you finish the associate, you can go next.
Yeah, and online. 3 to 5, yeah.
Online.
Yeah, we don't gotta come to school. Yeah, we don't have to come on campus.
Okay. Okay, you don't want to learn from me, okay.
No, you can
Okay. Okay, all right. Okay. But I don't get paid for that, but it's okay.
Love you to ship you stuff and your followers get paid.
Not really, because I only have a little bit. But we will see. Okay. So energy, we talked, this is a really important concept. And how energy cannot be created or destroyed, but it can change from one form to the other. I gave you the example with the car. You put in gasoline, that's an example of fuel chemical energy. Then there's the ignition, ignite, ignition, fire. Then in the ignition, it's gonna turn on the ignition is gonna do a combustion, and then there will be an explosion. So all the chemical energy is now gonna turn into thermal energy or heat energy. Then the thermal or heat energy is going to revolve the pistons in the transmission, leading to the wheels to spin, and now that's a kinetic energy. So we changed energy from one form to the other. We talked last week about thermal energy. When we are so cold, how do we achieve shivering thermogenesis. So in shivering thermogenesis, when we are so cold, hmm? Yeah, when your body is so cold, what happens? The electric signals from your brain start. So now you have electric energy with the electrolyte. The electric energy in the form of action potential will go to your skeletal muscles and cause vibration. It causes vibrations in the skeletal muscles. Then when the skeletal muscles vibrate, what kind of energy is that? Is it still electric energy? Kinetic energy, very good. Then the kinetic energy now is going to harvest for us ATP, and that's chemical energy. Then we use the chemical energy as fuel to burn that chemical energy to warm ourselves. So that's shivering thermogenesis. Shivering thermogenesis. Okay. So we said there's potential energy, and that's the energy stored in an object, but not currently doing work. And an example of that would be the water behind the dam. And there's chemical energy, that's the potential energy in the molecular bonds, like in ATP. We talked about how we cleave ATP from adenine triphosphate into. So how do we hydrolyze energy from ATP? We have adenine nucleotide with how many phosphates? 1, 2, 3, triphosphate. Then we break one bond, and then we end up with PI, and one is gone. So when you break this bond, energy gets out. So that's a form of catabolism. We get energy when we catabolize. When we break the bond, energy is liberated. And that's how we get chemical energy. That's how we utilize chemical energy. So that's the chemical energy in the bonds. So that's an example of an endothermic reaction. We break the bond to get energy. The opposite is an exothermic reaction, where we form the bonds in anabolism, but that is now gonna consume energy. Okay? Then, so that's the concept of chemical energy. Then there's free energy, delta G. Free energy is the potential energy available in a system to do work. And there's kinetic energy. Kinetic energy is the energy of motion. So the chemical energy is a form of potential energy, but is found in the chemical bonds. And then there's kinetic energy. Kinetic energy is the energy of motion and the energy of doing work. And examples of that would be the muscle movements. So you see, when we move the muscles, that's a form of kinetic energy. Then there's the flow of ions and the vibration of the eardrum. And heat is represents kinetic energy of the molecular motion. Kinetic energy of the molecular motion. So when we move our muscles, when they vibrate, when we shiver, what happens? We would generate heat. There's also electromagnetic energy, and that's the kinetic energy of the photons. And there is electric energy that has both potential and kinetic forms. So what are the classes of chemical reactions? So a chemical reaction is the basis for many biochemical pathways that happen, especially in metabolism. How am I going to be able to metabolize very important nutrients and get ATP, chemical energy, out of them? So a chemical reaction is a process in which a covalent or ionic bond is formed or broken. So a chemical equation will symbolize for us the course of a chemical reaction. So you have reactant on one side, then the arrow is pointing to the products. So you had reactants that will later on develop into products. Classes of chemical reactions include, there's decomposition reactions, there's synthesis reactions, and there's exchange reactions. That's very important. So we have synthesis reaction where A plus B they combine together to give us AB, a really big molecule. And we saw this in the peptide bond formation. One amino acid plus one amino acid, and then we have dehydration, and then water leave, then you have a peptide bond. And we have the opposite. We can have A plus B falling apart to give us A and B alone. So now we remove, after we remove water to do a peptide bond, we can, after we perform anabolism to do a peptide bond, we can do catabolism and break that peptide bond, and then we separate both amino acids. So this is an example of a synthesis reaction, and this is an example of a decomposition reaction. And then there's exchange. In exchange, you would have AB reacting with CD, and in the end, you end up with AC plus CD. So now you have exchange. You have exchange. So now it's no longer, the A and B are no longer together. C and D are no longer together. You have exchange them.
Is
You
it
have
the same as replacement?
replacement too, yeah, yeah. So there's replacement, there's exchange. So they change the name, but the concept is the same. So that's what we see here. So in decomposition reactions, what happens is the large molecule breaks down into two or more smaller ones. So you have AB disintegrating into A plus B. That's a large one decomposing. Then in synthesis, you have the opposite. You have A and B who are decomposed. They come together, two or more small molecules combine to form a larger one. Then you have exchange reaction. So in exchange reaction, two molecules exchange the atoms or groups. So you have AB plus CD, then they will replace, as you said, and you would end up with AC plus BD. So an example would be stomach acid, HCl, and sodium bicarbonate, and then you would end up with NaCl salt. So the Na is going to leave the bicarbonate. You're going to have NaCl, and the H is going to attach to the H2CO3. Decomposition reaction. In the decomposition reaction, they fall apart. So the starch molecule breaks into pieces, and then you would go from a starch molecule into glucose molecules. Okay. Synthesis reaction. You have amino acids that are dots and small, and then the amino acids, they're going to combine together to give you a polypeptide. So that happened through the actions of a peptide bond. So a peptide bond was formed to give a synthesis reaction. Then there's exchange reaction. In exchange reaction, what happens is you have A, B, and C and D, both are separate. Then they exchange, you have A and C and B and D. Okay. Classes of the chemical reactions. So we classify chemical reactions on the direction of movement. So there are reversible reactions, and then there are irreversible committed reactions. So the reversible reactions can proceed in either direction under different circumstances. And that is symbolized with a double-headed arrow. So here, this is for the removal of carbon dioxide from the blood. So if there is a lot of carbon dioxide in the blood, the reaction is going to shift this way to remove the carbon dioxide. Otherwise, I will have acidosis. But if there is a drop in carbon dioxide and the acidity goes down, and now we're really basic, then the reaction is going to shift to the left to supply more carbon dioxide. That's very important in the respiratory, urinary, and the digestive physiology. And we're going to get to that. So reversible reactions follow the law of mass action. And that is the direction of the reaction is determined by the relative abundance of substances on either side. So that if there is a lot of carbon dioxide on this side, what's going to happen to the reaction is going to shift away. It's going to shift away from the direction of the stress. If there's a lot of carbon dioxide, it's going to shift to this direction. If there's a lot of bicarbonate, it's going to shift into this direction to donate hydrogen protons. And equilibrium is reached when the ratio of the products to the reactants is stable. Reactions occur when molecules collide with enough force and correct orientation. So the reaction rates increase when the concentration of the reactant increase. Like I said, if we increase carbon dioxide, we're going to have more product. So the rate will increase the speed. So the rate of the reaction is another way for saying the speed. The speed of the reaction is going to increase when I increase the concentration. When I increase the temperature, when the temperature increases, what does the temperature do? Temperature is the average kinetic energy representing the movement of the molecule. So if you have a molecule under temperature 100 degrees Celsius, another one 70 degrees Celsius, then you have a third one 50 degrees Celsius. So the less temperature representing the less kinetic movement, and the more temperature. That's why when you have cold ice, it has the lowest temperature. You put it in the stove, and then it becomes liquid, then it's a little bit more hot, then it's moving some more. Then when it's gas, it's really flying in the air now. Then a catalyst. A catalyst is really important. That's an enzyme. So what does the catalyst do? A catalyst speeds up. A catalyst speeds up a, I have it here. So a catalyst speeds up the reaction. How? By bringing down the activation energy barrier. So if I have this coordinate system, and in the coordinate system I have time, as time goes on in milliseconds, then I have concentration on this side, and I begin with reactants. I have reactants. The reactants are gonna have to take a path to become products. What the enzymes do is they lower. So this is known as the activation energy barrier. So the reactants are here, and they have to climb all the way up this activation energy, EA, this activation energy barrier, cross it in order to become product. They have to go uphill. What the enzyme does is it lowers the activation energy barrier, makes it really low, and now the reactant only has to climb this much. So what will be faster? Going from reactants to product in pathway A, or going from reactants to product in pathway B? B. So by lowering the activation energy barrier, the catalyst or the enzyme, catalysts or enzymes speed up the reaction by, they have an active site. So this is the enzyme. This is the enzyme. It has an active site, and the active site can take the reactants and convert them into products. Okay? They lower the activation energy barrier. Activation energy barrier. And that will lead to the reaction going faster. EA, activation energy, is known as EA. Okay. Catalysts are not changed. Many people think that while this reaction is going on, the catalyst is gone. It is used in the reaction. It is not changed. And the catalysts do not change the reaction. So if this reaction tells me to go from A plus AB plus BC, then exchange into AC plus BD, it's not, the catalyst is not going to change it. It will just make it faster. So if you do a reaction without the catalyst, you will get this product. If you do the reaction with the catalyst, you will get the same product, but faster. So it will not change the product. And itself, after the reaction is finished, the enzyme is still there. It's not like it's gone when the reaction was done. So it will always be there. It just makes the reaction faster, and they bind the reactants and make arrangements. By the way, they break the bond between A and B, the bond between B and C. So they alter the reagents, but in the end, they give us the product that we need, and they provide a separate route. You see, the enzymes, the enzyme catalysts bind to the reactants and hold them in orientations that facilitate the reaction. Then we'll go to metabolism. We talked about metabolism and how in metabolism, all the chemical reactions of the body are divided into catabolism and anabolism. Catabolism is the energy releasing or exergonic. So exergonic when the temperature is released. So I break the bond like I broke ATP in there. That's an example of an exergonic. That's an exergonic, but endothermic, exergonic. So the exergonic reaction liberates for me ATP, but it used heat, so we call it endothermic. So it uses heat to break the bond, and then it gives us energy, exergonic, meaning exit. So the energy will exit. When I break the bond in catabolism, I break the bonds between the molecules, and when I break the bond with the molecules, I consume heat, I put in heat, that's why it's an endothermic reaction, but I get out energy, that's why it's an exergonic reaction. The opposite for anabolism. I connect the bonds by removing heat, that's why it's an exothermic reaction, but I do not get energy out. The energy does not get out. The energy is consumed in the reaction, and that is known as endergonic. Very good. Endergonic and exothermic. So let's look at catabolism. In catabolism, the energy releasing or exergonic is a decomposition reaction, and it breaks the covalent bonds and produces smaller molecules. But in anabolism, it's the opposite. It's endergonic. Endergonic, yes.
So like the exergonic reactions, all of them they're endothermic.
Yeah, because why do we use endothermic? The endothermic is I use heat to break. How do I break? I use heat. So if I have two molecules, I want to break, I supply heat. So I put heat in. So when I put in, that's thermic. That's thermic. Thermic. What kind of thermic? That's endothermic. So I use heat. So the delta H heat goes up. I use heat to break the bond. But when I broke the bond, energy came out. And that is energy exited. That's exergonic. And the opposite. If I want to build the bond, now I don't break the bond, so delta H is going to go down. So that's going to be exothermic. So now is going to be minus, exothermic minus, endothermic plus. So the exothermic is going to be minus, and then the energy, the heat is going to leave, but we're going to need energy we're going to need to consume energy in order to build the bond. So we consume energy to build the bond, and we release energy when we break the bond. So we use an endothermic reaction to get exergonic energy, and we use exothermic reaction to get endergonic energy. So when we need energy, do we go for anabolism or catabolism? We go for catabolism. And in catabolism, we get energy by, how do we break the bond in catabolism? Do we break the bond by endothermic or exothermic reaction? Endothermic. And when I do an endothermic reaction to break the bond, do I get an exergonic or an endergonic? Exergonic. Very good, very good. So anabolism is the energy storing. Endergonic synthesis react, they require energy input. You see, they require energy input, and that is the production of protein or fat from amino acids. From little stuff you get big stuff. That is known as anabolism. So catabolism and anabolism are inseparably linked. So anabolism is driven by energy released from catabolism. So we get the exergonic energy to build up the endergonic reactions. Okay, so they supply each other. Metabolism, oxidation. So a chemical reaction. So oxidation, we talked about oxidation and reduction, and that is oxidation is a chemical reaction in which a molecule gives up electrons and releases energy. It gives up electrons and releases energy. And the molecule is oxidized when it loses the electrons. So now we got to talk about the oxidizing agent and the reducing agent. The oxidizing agent is the electron acceptor. While the reducing agent is the electron donor. So when we look at sodium chloride, NaCl, separating into Na plus Cl minus. So lose electron oxidation. Who's oxidized? Sodium or chloride? Sodium. Who's oxidized? Sodium or chloride? Sodium. That's oxidized. If it's oxidized, then it will be the reducing agent. The reducing agent. What about chloride? Chloride is reduced because it gained an electron. Leo says GER, gain electron reduction. So the chloride is reduced. When the chloride is reduced, it is also the oxidizing agent. So you are the opposite agent of what happened to you. If you are oxidized, then you are the reducing agent. If you are reduced, then you are the oxidizing agent. Oxidation of one molecule is always accompanied by a reduction of another. That's why they are called a coupled oxidation reduction reactions. Okay, so now we have the carbon compounds. Carbon compounds or organic compounds or organic chemistry is the study of compounds containing carbon. And we said that earlier today when we were talking about the atoms that make up our life. We said oxygen is important for aerobic respiration, is important for oxidative phosphorylation. We talked about phosphate, it works as a buffer and a phosphate salt. We talked about nitrogen, it works also like a buffer, it accepts hydrogen protons. And we talked about carbon, we said it is an organic compound and it participates in the making of the organic compound. So we use carbon to make carbohydrates. You see that carbon is one of the atoms to make carbohydrate. We see that lipids are made up of carbon too. Proteins are made up of carbon. Remember earlier today when we were drawing the two different types of amino acids that need to be connected. They had an alpha carbon. They had an alpha carbon. They had a carboxylic terminal. That's another carbon. They had an R group. It has another carbon there too. So all of these carbons represent that carbon is an important part of carbohydrate. Lipids now look a little bit different. Lipids have a glycerol backbone that is attached to a carboxylic group, and then you have a long chain of carbons, a long chain of carbons. That's the glycerol backbone, and these are free fatty acids. But you see there's still carbon all over the place. So that shows you that carbon doesn't only make proteins and amino acids, it also makes glycerol backbone, free fatty acids, and lipids. For proteins, we already talked about how the building block of a protein is an alpha carbon that has hydrogen on each terminal. It has amino terminal. It has a carboxylic terminal, and it has an R group. It has an R group. So you see there's a lot of carbon. And nucleic acids like ATP, adenine triphosphate. Adenine has a lot of carbon. These are all carbon groups. So you see that carbon is an integral part to all the compounds that we utilize in life, whether carbohydrates, lipids, proteins, and nucleic acids. So the carbon is uniquely suited to form a variety of structures. So it has 4 valence electrons. Carbon has 4 valence electrons and can form 4 covalent bonds with other atoms, and can bind readily with other carbon atoms to form carbon backbones. There are long chains, branch molecules, and rings, so it readily bonds with hydrogen, oxygen, nitrogen, sulfur, and other elements. Carbon backbones carry a variety of functional groups. So there's a small cluster of atoms attached to carbon backbone, and they determine many of the properties of organic molecules. For example, hydroxyl, methyl, carboxyl, amino, and phosphate groups. So these are the groups that are functional groups that attach to carbon. So we see that carbon is attached to these multiple functional groups. Carbon could be attached to OH, that is found in sugars and alcohol. Could be attached to a methyl, it could be found in fats and oils, steroids, and amino acids. And then it could be attached to carboxylic groups, and that is part of the amino acids. Carbon can also be attached to an amino group representing an amino acid, and carbon can be attached to phosphate, representing that there is this bond between phosphate and carbon, and it shows you that not only is carbon important, but it has versatile ability to bind all these different functional groups. So OH is a functional group found in alcohol. Methyl or methane is a functional group that is found in fats, oils, steroids. And a carboxylic acid or carboxyl group, where you have this carbonyl group attached to an OH, it can also bind carbon. So you see that carbon can bind all of them. Do you see this point? That carbon can bind OH, CH3, COOH, NH2, phosphate. So now it can, that's why it's important for the metabolism of all of these different molecules, whether lipids, proteins, nucleic acids, lipids, proteins, nucleic acids, and carbohydrates. So macromolecules are large organic molecules with high molecular weights. So most macromolecules are polymers. So they are long chains, long branches, and molecules made of repetitive series of identical or similar subunits called monomers. So the monomers may be identical or different. So for example, starch is a polymer of about 3,000 identical glucose monomers, and DNA is a polymer of 4 different nucleotide monomers. So polymers formed by polymerization or the joining of monomers. Okay, so what does that mean? So in order for me to have a macromolecule, this macromolecule has to be assembled from micromolecules. So the macromolecule is assembled from micromolecule. So we would have a macromolecule such as, let's begin, we already discussed proteins. So proteins, you'd have a long chain that is made up of multiple amino acids. Sugars, you have a polysaccharide that is made up of disaccharides, and it can be broken down to some more to monosaccharides. In addition to the proteins and the polysaccharides, we have lipids or fats. Lipids and fats can be broken down to glycerol and free fatty acids. This arrow pointing down represents catabolism. So we are breaking down catabolism. While going the other way around from glycerol and free fatty acids to lipids, that is known as anabolism. Same thing when we're going from monosaccharide to disaccharide to polysaccharide, or from amino acids to protein. So here we are learning that these macromolecules, the ones on the top, we ingest them. We ingest them in the form of macromolecules. But our digestive system job is to break them down physically, so it churns them down. Then it has enzymes, and then the enzymes will break them down chemically. So first of all, we have mechanical digestion, physical digestion, chopping things up. Then after physical and mechanical digestion, what do we have? We have chemical digestion. So now we go from, so your stomach can cut down proteins to amino acids, cut down big proteins to so you have proteins that are really aggregated. The digestive system, through physical and chemical digestion, can break them down into digestible pieces of protein. Same thing with polysaccharides, something with lipids. But to go from protein to amino acids, you need an enzyme. That's why we have peptidases that break the peptide bonds. And that also we have, to break down the bond between the polysaccharides, we have amylase, that's a different type of enzyme to digest sugars. And then we have, for the lipid, we have lipase to break down the lipids. So polymerization is a form of anabolism. So I polymerize, I start building up, I start making more and more, to make more, a very long chain of polymers by adding up these little monomers. And that is through condensation. And hydrolysis is the opposite of the dehydration synthesis. And that is known as splitting a polymer in monomers by adding the water. So the enzyme helps break the covalent bond. The covalent bond. So we split a polymer in a monomer by adding water, and the enzyme helps break the covalent bond that links the two monomers together. So a water molecule ionizes into OH minus and H plus. So OH minus is added to one monomer, and H plus is added to the other monomer. You see, these are two monomers. We add them together by the removal of water. So that's dehydration, as your friend nicely said earlier today. So you see water came out, and then you have a dimer. You had a monomer, then you had a dimer. In the case of sugar, that's a disaccharide. These are two monosaccharides attached together as disaccharide. So that's the dehydration synthesis. In hydrolysis, I add water. So in hydrolysis, I add H plus to one side, and I add OH to the other side, then I separate, going from disaccharides into, I go from disaccharides into monosaccharides. Now we're going to move on to carbohydrates. So carbohydrates are hydrophilic organic compounds. So these hydrophilic organic molecules, they have this general formula. That's a very unique thing about them. All the carbohydrates look like that. They look like CH2O times N. So we've seen how the polypeptides look like. The polypeptides look like multiple carbons attached, multiple alpha carbon connected to each other at the amino and carboxylic terminal. And you have OH here, you have OH here, you have OH here. Then you have an H group, H group, H group, then H group. Then you have an R group, R group, R group, R group. And they all are connected by a peptide bond, peptide bond. The sugars don't look like that. Sugars look like CH2ON. What does that mean? That means you have a carbon group with an H, with two H's, with three H's, and O, then another carbon group, H, 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 then an O. It's like that. So they're going to keep on going. Depends. Some of them, there's 3 connected. Others, you have 4. Others, you have 5, and so on. So that's the basic formula for polysaccharide, for carbohydrate, for sugars. So sugars are different from protein. And proteins are connected by polypeptide, and sugars are polymer. So sugars are polymers. And proteins are made up of polypeptides. Polypeptides. Okay. So now let's look at glucose. Glucose, N is a 6. So that means you will have 6 carbons, 6 times 2, that's 12 hydrogens, and 6 times O, that's 6 oxygens. It's very nice to know the formula for glucose. You're going to keep seeing it. So you know already that the building block for carbohydrates is C water, CH2O, and a parentheses close, you have an N. If you want to make a glucose, you turn the N into a 6. Then you multiply. 6 times 1 carbon, that's 6 carbons. 6 times H2, that's 12 hydrogens. And 6 times O, that's 6 oxygen. So there's 2-to-1 ratio of hydrogen to oxygen. There's 2-to-1 ratio of hydrogen to oxygen. So for every oxygen, there's 2 hydrogens. And the names of the carbohydrates often built from the root saccharose or O's, like maltose, fructose, glucose, lactose, galactose. That's actually very important. So now we have 3 types of disaccharides. So when you drink milk, or when you eat oatmeal, or when you eat some form of table sugar, you have 3 types of sugar. You can either have sucrose, or you can have maltose, or you can have lactose. So these are the 3 types of disaccharides that are there. So these are disaccharides. These are all disaccharides. So that means they are made up of 2. They are made up of 2 monomers. 2 monomers. 2 monomers. They are made up of 2 monomers. 2 monomers. They are made up of 2 monomers. What is sucrose? Actually, there's something in common between all of them. All of them have glucose as a monomer. 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 Sucrose has glucose and fructose. Maltose has glucose and double glucose. So that's the interesting one. Maltose has double glucose. While lactose, the sugar of the milk, that's glucose and galactose. Excellent. Galactose. This is the sugar of milk. This is the sugar of oatmeal. and this is the sugar of sugar cane. So when you eat sugar, we're gonna first, up here, I didn't draw it, but up here you have a polymer. Then from the polymer, you have disaccharide, then the saccharides are broken down into their monomers. When I break them down into their monomers, what's the next step? When I break them down into their respective monomers, what is the next step?
You're gonna break that down?
So the glucose now is ready to go into, give me ATP. And we do that by glycolysis. By glycolysis. Glucose can give me ATP by glycolysis. Glucose can give me ATP by glycolysis. What about glucose here can give me ATP? So maltose is the best sugar because it is so convenient. That's why people have, it's healthy to eat maltose, oatmeal, ATP. What about fructose? Can I send that into glycolysis? Does glycolysis take fructose? That's like going, you have dollar and you go to France and you say, I want to use dollars there.
No.
So the only currency for sugar in the cell is glucose. What's going to happen to fructose and what's going to happen to galactose? I'm sorry? Break down again. No. The cell has enzymes that reverse sucrose into glucose. They can interconvert fructose into glucose. Interconvert galactose into glucose. Then glucose can go into glycolysis. So either you are glucose, you're ready to go into glycolysis, or you could be fructose. We need to convert you, rearrange you. Remember isomers? Talk about isomers earlier. So fructose and galactose are isomers of glucose. So now we're going to rearrangement to make them look just like glucose. Then we shuttle them in glycolysis. Clear? Okay. So these are monomers that we talked about, that glucose, galactose. So are the simplest carbohydrates. We have one more half hour. So we talked about most of the stuff. Maybe we didn't read this word by word, but we have covered all the topics. Okay, so when the study guide comes out, just go through the slides, see which slides you can use to help you answer the questions for the exam. Okay, monomers are of larger carbohydrates, and there are three important monomers. These are glucose, galactose, and fructose. They're produced by digestion of more complex carbohydrates, and glucose is known as blood sugar. And all three have the same molecular formula, and they are isomers of each other. We just said that. Ribose and deoxyribose are the monomers. Okay, so that shows you glucose. You see, that's glucose, that's galactose, that's fructose. They have the same compound, but they are just arranged differently. So that makes them what? Isomers of each other. Very good. Very good. Disaccharides. Oh, we just did that. Sucrose, table sugar. Sucrose, table sugar is glucose and fructose. Lactose, milk sugar. That's glucose and galactose. We talked about that. Maltose are glucose and glucose. These are oligosaccharides. You see, they are bound together. They are oligosaccharides are short chains of 3. Oligosaccharides are chain of 3 or more monosaccharides. So they have to be at least 3. So that's why maltose is a disaccharide. But if you go one more, we don't say trisaccharide. We just say oligosaccharide. You see lactose, they always have an O in the middle connecting them. They have an O in the middle connecting them. So polysaccharides are long chains of monosaccharides, about 50 or more. And there are three important polysaccharides. There's glycogen, starch, and cellulose. So glycogen is the energy storage form in the liver. We talked about that. It's not only found in the liver, it's in the liver, the muscles, the brain, the uterus, and the vagina as well. And the starch, is an energy storage. So starch is used for energy storage in plants that is digestible by humans. And cellulose, in cellulose, the structure is a structural molecule in plants that is important for human dietary fiber, but indigestible to us. You see? Functions of carbohydrates. So they are quickly mobilized source of energy, and all digested carbohydrates converted to glucose and oxidized to make ATP through the glycolytic pathway. And they are often conjugated or bound to lipids and proteins. Examples are lipids. Proteins of the cell membrane have chains of up to 12 sugars attached to form the glycolipids and the glycoproteins respectively. And glycoproteins are a major component of mucus. There are what is known as proteoglycans. So proteoglycans are macromolecules that are more carbohydrate than protein. And they form gels that hold cells and tissues together, and they fill the umbilical cord and the eye, and they are there for joint lubrication, and they are responsible for the rubbery texture of cartilage. There's a moiety. A moiety is each component of a conjugated macromolecule. So the region where you have, when you have glycoprotein, so when you have a sugar attached to the protein, that's the moiety. The moiety is the additional part that we assemble into our macromolecule. Then we move on from, we finished proteins and we finished sugars. Now we move on to lipids. So we alluded to lipids already, that they are made up of a glycerol backbone that is attached to a free fatty acid chain. So lipids are hydrophobic organic molecules with a high ratio of hydrogen to oxygen. So there are more calories per gram than carbohydrates. So lipids are hydrophobic and they have more hydrogen than oxygen. That's what makes them saturated fatty acids. Unsaturated, they have less hydrogen and more double bonds. So there are 5 primary types of lipids in the human body. There's the fatty acids, triglycerides, the phospholipids, the eicosanoids, and the steroids. So fatty acids are chains of 4 to 24 carbon atoms with carboxyl group on one end and a methyl group on the other. And we have essential fatty acids that must be obtained from food. And there are fatty acids that are classified as saturated or unsaturated. So the saturated fatty acid carbon atoms linked, they are carbon atoms linked by single covalent bonds. And the molecule contains as much hydrogen as possible. Saturated, that's why we call it saturated with hydrogen. These are the saturated fatty acids. But the unsaturated fatty acids, they contain some double bonds between the carbons, and the molecule has potential to add hydrogen. So there are polyunsaturated fatty acids, and they have multiple double bonds between the carbons. Triglycerides is when we break the backbone, when we break the glycerol backbone, and we separate a glycerol, and then we have free fatty acids. These are known as the triglycerides. These are the triglycerides because there's 3 of them, triglycerides attached to each glycerol backbone. You see, that's what I was trying to draw earlier. So This is the glycerol. You see the three carbon backbone. 1, 2, 3. It has OH. Then these are the saturated or unsaturated fatty acid. Then we combine them together. You see how we combine them? We remove OH from one side and H from the other side, and then we connect them. You see, that's anabolism. We remove the OH. We remove the OH. We remove the H. We connect. So we remove the OH and the H on all of them, whether it's polypeptide, whether it's carbohydrate, whether it's fats or lipids. In the end, we use water to separate them, and we use water to condense them. So here we removed water, H2O, to connect them together. So that's an example of anabolism. If we want to build up, we stack them up together, we remove H2O. And if we want to break them down, we add OH to this group and we add H to this group, then we break them down. So it's very important for you to have a mental picture of what a protein look like, of what a carbohydrate look like, and what a lipid looks like. That's a lipid. A lipid has a glycerol backbone and free fatty acids. We join them together to make a triglyceride. We break them apart like that. So if I want to get energy, I do catabolism. I break this bond by adding OH to this side, H to this side. Then I shuttle this in a metabolic pathway to get ATP, and I shuttle each one of those to get ATP. Like when your phone, you remove the screen, and then you remove the motherboard, and you sell each one, and you make money off that. So the same thing here. If I want catabolism, I break down the but you need to know where is glycerol. So you can say, I don't know the structure of a protein. If I ask you on the exam, where do you find a glycerol backbone? I don't know. That doesn't make sense. I'm not telling you to draw this on the exam. I will never ask you to draw linoleic acid, this one. I will never ask you to draw linoleic acid or stearic acid or even glycerol backbone. But I expect you to know that free fatty acids, I find them where? Do I find them in carbohydrates? Do I find them in nucleic acids? Do I find them in amino acids? That one you need to know. You need to know the major structure. You need to know a peptide bond. How do I get a peptide bond? Where does that happen? Does it happen in carbohydrates? Does it happen in protein? Okay? So that's the major kind of stuff. That one is the one you need to know. So a trans fat is a triglyceride with one or more trans fatty acid groups. You guys okay, or you want to leave? Okay, all right, go. You look tired. Go. Bye. Okay.